All right, so here is the vertical help sheet. Um, Problems here that we're supposed to be looking at. We're supposed to be drawing a free body diagram for each one of these at the top and the bottom of the circle. Okay, so one thing to keep in mind is these are all circles. So there's always going to be a centripetal acceleration. There's always going to be a net force. That centripetal acceleration will always point towards the center of the circle, and that centripetal force will always point towards the center of the circle. So, ball on a string. Here we go. So if we start at the top, there's our ball. Okay. We're going to have a force of gravity down. And then the string is also going to be pulling the ball down. So there's going to be a tension in that string there. The centripetal acceleration will point towards the center of the circle. Since the ball's at the top, it's got to point down. At the bottom of the circle, here's our ball. We'll have a force of gravity here, but since the ball is now at the bottom of the circle, the tension in the string will be pulling it up. It will be greater than gravity, and so we get a centripetal acceleration up. Now, here's something that's important for you to realize, or for something for you to understand, is we need to understand where's the tension in the string going to be greatest, at the top of the circle or the bottom of the circle. If you need to, go to the front of my room. There's a ball on my ball on a string is up there. Swing it around a little bit and feel where the tension in the string is greatest, at the top of the circle or the bottom of the circle. You should be able to feel when the tension is pulling on your hand the strongest. All right. So either come up with a theory or swing the ball around. Do that now. Hit pause and figure out which one is going to be the bigger tension. All right, so the answer is it will always be a greater tension at the bottom of the circle. The reason for that is the centripetal acceleration must stay the same. So here at the top, these two forces are added together to equal the centripetal acceleration. Sorry, that was centripetal force, excuse me. Down here, we still have to add these two forces together, but now force of gravity is negative because it's pointing away from the center of the circle, whereas above it was positive, it's pointing the same direction as the tension. And so the tension must be bigger at the bottom to account for that, because we have to keep the force of the centripetal force the same, because it's going to be moving at a uniform speed, and so the tension at the bottom is always stronger. All right, so I'm going to erase this, get this out of the way so I can do the child on the Ferris wheel. Hold on, let's get this erased. Okay, here we go. Child, Ferris wheel. Here we go. At the top, we've got our child. He will have a force of gravity acting down on him. There will be a normal force up, because we're at the top. The centripetal acceleration will be down because we're at the top of the circle here. So the force of gravity will be greater than the normal force. Okay. If it wasn't, if the normal force was equal to the force of gravity, the child would move in a straight line, not in a circle. Now, down at the bottom of the circle, we'll still have a force of gravity down, and our normal force will be up. And you'll notice our normal force got bigger, and that's because of the inertia of the child at the bottom is actually pushing harder against the chair, so the chair pushes up harder, and also we need an acceleration up because it needs to point at the center of the circle. And we get a centripetal acceleration up. You'll notice also that F norm and FG switched their signs. Up here, this is a positive force and this is a negative force, because F norm is pointing away from the center of the circle, FG is pointing towards it. At the bottom, F norm is positive because now it's pointing towards the center of the circle, and FG is pointing away from it, so it is negative. All right, passenger on a hilly road. So we're going to assume the road looks something like this. and this would be the top, this would be the bottom. Assuming these are half circles, so it's still circular motion. Okay, so at the top, what we get is, here's the car. We're going to have a force of gravity down. The road underneath, of course, is pushing up. Force of gravity has to be bigger again so that we can get an acceleration, or centripetal acceleration. At the bottom, we'll have our force of gravity down. We'll have our normal force up. It will need to be greater so that we get the centripetal acceleration again. All right, pilot in the loop-de-loop. So if you don't know what the loop-de-loop is, it's just simply the pilot, if he's flying like this, he just does a loop, like so. Okay, so this one, though, is a little bit strange because we have to think about this for a little bit. So if we have our pilot, there's our pilot right there. He's going to have his force of gravity down, but he's upside down at this point. So the airplane is actually above him if you're looking from the ground, because he's upside down in the loop-de-loop. So the airplane, the chair, the bottom of the airplane, the cockpit, whatever you want to call it, is actually pushing him down. That means that that's the normal force. In this case, the normal force is actually pushing him down, and so we get our centripetal acceleration down this way. At the bottom, okay, of the loop-de-loop, still got his force of gravity down, but now to keep him in a circular motion, F norm, now it's got to be bigger, and so we get the centripetal acceleration up. All right, car and Hot Wheel track loop. So the car just goes through the Hot Wheel track and we make it into a loop, so it's going around a loop. It's very similar to the pilot in the loop. So if we do the top of the loop, all right, car is going to have a force of gravity acting on it. Again, the track is above the car, so the track will push the car down. So that means that the normal force is down again. At the top, we get a centripetal acceleration down, which makes sense. At the bottom, force of gravity will be down. The normal force will be up, because then at the bottom of the track, the track is under the car, and so we get a centripetal acceleration up. Twirling a bucket of water. Okay, so this is where you just put some water in a bucket and you swing it around over your head. I've actually done a video of this demo. You'll want to watch it after you go watch the weightless discussion video. So you'll want to kind of wait until you hit that to actually see this demo. But here is your bucket of water above my head. It's got a force of gravity on it. The bucket will be, again, above the water. And so the bucket will be pushing the water down. And so that, again, is a normal force. And so the normal force will give us a nice centripetal acceleration down. Now, at the bottom of the circle, we will have a force of gravity and a normal force up. Notice that at the bottom, the sketch looks very similar every single time. What's different is what it looks like at the top of the circle, and we'll kind of get into that a little bit more as we go. All right, we got two more. We've got a roller coaster loop and a roller coaster at the top and bottom of a hill. So if we do the roller coaster loop first, so it's going, again, it's going through the loop-de-loop. So the top would be here, the bottom would be down here somewhere. So at the top, we'd have a force of gravity. And of course, now the track is above the roller coaster again, so the track will be pushing down, and that would be the F norm. and we get a centripetal acceleration down. All right. At the bottom, it will pretty much look like the rest of them. We'll have a force of gravity down. The normal force will be up. And we will get a centripetal acceleration up. Now, for the roller coaster, the top and bottom of a hill, again, we're pretending that the hills are like half circles. So this would be the top right here. This would be the bottom down there, somewhere like that. So at the top, now we're going to have a force of gravity down. Now the track is underneath the roller coaster, so F norm will be up again, and we'll have a centripetal acceleration down because gravity has to be bigger here. Otherwise, it doesn't travel in a circle. And then at the bottom of the hill, we'll have a force of gravity down. We'll have the normal force up, and it has to be up because it's circular motion, like we said. And there's our centripetal acceleration. So, you may have noticed that there's a pattern here. And the pattern can really be broken down into two things. There's really just two types of vertical circles. The first type is a ball on a string. Whoops. Sorry. Wrong thing there. Ball on a string. So a ball on a string is one type of a vertical circle. The other type is a Ferris wheel. Okay? So both of these can be used as a template for every vertical circle. Every vertical circle can either be treated like it's a ball on a string or it can be treated like it's a Ferris wheel because it follows the same pattern. Okay? So really what one of your goals here is to figure out, is it a ball on a string or is it a Ferris wheel? So take a look at the ball on a string and a Ferris wheel and the rest of our free body diagrams and see if you can figure out which ones are ball on strings and which ones are Ferris wheels. Okay? Go ahead and hit pause and do that now. All right. So if you're coming back, here is how you tell if it's a ball on a string or if it's a Ferris wheel. A ball on the string at the top of the circle. So you notice at the bottom of the circle, they all look the same. All the sketches look the same, so there's no real way to tell the difference. What is true is at the top, they look different. A ball on a string has two forces down at the top of the string. Or excuse me, at the top of the circle. A Ferris wheel only has one force down at the top of the circle, and that one force is gravity. So, difference. Ball on a string, two forces down. You'll notice no forces away from the center. All right. And Ferris wheel, there's one force down and one force away from the center. So if we go ahead and look at these, pilot in a loop-to-loop would be a ball on a string. Car on a Hot Wheel track is a ball on a string. Twirling bucket of water is a ball on a string. The roller coaster loop is a ball on a string. The others are Ferris wheels. So a passenger in a car on a hilly road, that's a Ferris wheel. One force down, one force up. And the roller coaster at the top and bottom of a hill is also a Ferris wheel.